Good morning, all of you. I am Vadaganathan. I am working as assistant professor in Erode Engineering College. We are going to see the topics of sorting, then graphs and networks, algorithms on graphs, route inspection, and traveling salesman, linear programming, simplex algorithm, and critical path analysis. These are all the overview of our session. Actually, we are going to find the best path by using graphs. Over graphs, we are going to find the best path by using different types of algorithm in DAA. First of all, we have to know the concept of minimum spanning tree. Minimum spanning tree is the spanning tree such that its total length of its arc is small as possible. That is what we are calling as a minimum spanning tree. In another way, minimum spanning tree is a subgraph which includes all the vertices and tree. That is what we are calling as a minimum spanning tree. Then we have to know subgraph. What is subgraph? Subgraph is a graph which each of which vertices belongs to graph, and each of edges also should be belongs to graph. That is what we are calling as a subgraph. Then tree is connected with the graph, and it does not contain any cycles. That is what we are calling as a tree. Then the concept of graph is connected if all of its vertices are connected. That is what graph is connected. In a graph, we will be having collection of edges and nodes. Then two vertices are connected. That means that there is a path between them. That is what if there is a path between two nodes, that we can say the path is available between two nodes. Then in another way we can see the path is a walk of walk in which no vertex is visited more than once. Also we have to know what is walk. A walk is a route through graph along edges from one vertex to next. That is what we are calling as a walk. So we will go with the next slide. Before we going that, we have to clearly understand that what is minimum spanning tree is sometimes also call it as minimum connector. Minimum spanning tree is the total length of arcs is small as possible. That is what minimum spanning tree. These are all the algorithm we are having in minimum spanning tree. First algorithm is Kruskal algorithm. Actually, in Kruskal algorithm, we have to list the what are all the edges in the graph. So after listing the edges, we have to check whether the list are in proper ascending order. We just sorting the edges based on the weight of the each edges, so that we can easily identify the minimum spanning tree of the graph. So we this is what we are calling as a Kruskal algorithm. Kruskal algorithm is for finding the minimum spanning tree, as well as it is first of all first step of Kruskal algorithm is sorting all the edges which is in the ascending order of the weight. After that we are selecting the arc which is we are selecting the edges which is having least edge. Also in the next next step is we are going to select the next leaf. It may if the particular edges which is I am going to select, the next edge should not create any cycle over there. If it is any cycles are available or cycles are going to occur, there is a chance of cycle in the graph. We have to avoid those edges the minimum spanning tree. So while applying Kruskal algorithm, we have to kindly ensure that whether we are occurring with the cycle or not. If it is there is a chance of cycle, you have to carefully remove that. Also while adding the tree, we have to ensure that there is no cycle. Then there is a choice of equal arcs. Then in each turn. Then we have to repeat the third step for multiple times, whether all the vertices are visited or not. So the crucial algorithm is a very easiest one. So now sometimes we will be called the crucial algorithm as a greedy algorithm. Greedy algorithm in the sense it just shorting the edges, and based on the edges we will do the ascending and ascending the edges, and we will do the minimum spanning tree. Uses of minimum spanning tree is cluster analysis. The maximum we are using cluster analysis in big data. Then big data or classification algorithms, real-time face tracking and verification. It is mainly used by our minimum spanning tree. Then protocols in computer science to avoid network cycles, entropy based image registration, then max bottleneck bots, dithering. These are all the real time example of our crucial algorithm. So this is the example graph of a crucial algorithm. Now, actually we will here we will be having nodes are D, E, A, B, C likewise. Here I am just connecting the here the nodes are connected with each edges by with the weight. Each edges will be having weight. For example, D to E having 4, E to A having 5, A to D having 6, A to B having 7, B to D having 6. Likewise we will be having nodes. So we have to we have to start with the small edges. First of all, here we are starting with small edges, that is D to E, because it only having very small edges compared to all of this D to E, A to E and A to B. Which one is a very minimum edge, in the sense D to E is a very minimum edge. So I am just taking D to E as the very least edge. Next least edge is E to A. Here D to E minimum edge is 4, E to A minimum edge is 5. So we taken E to A minimum edge as 5. Next, we have to identify next minimum edge. What is the next minimum edge? Next minimum edge is actually already we will be having B to C. Next minimum edge is A to D, but there is a chance of creating cycle over here, right? So we are not supposed to take cycles over the graph. So here we just considering the next path, that is our B2C. B2C is the another least edge. So it will be considered for shorting the creating the minimum edges. So B2C will be considered the next. Then before that, if I am choosing if I am choosing A to D will be creating a cycle. So we does not consider that that path A to D edge is 6. So we don't need to consider that, but we can consider D to B. Just check here I am just putting D to B. So it's just connected all the graphs with minimum edges, right? It just connected all the graph A to E. First of all, I have connected the edge D to E, that is our 4. Next I have connected first edge is connected with D to E, that is 4. Next edge is connected with E to A, that is 5. Next we have connected D to B, that is 6. Then B to C, that is 5. So here Kruskal algorithm is mainly exclusively using for identifying the minimum spanning tree. These are all the steps we have given. First step is sort all the arcs into ascending order of weight. First of all, we have to sort all the edges. After that, we have to select the best edge. We have to select the best edge in the sense we have to select the least edge which is available over the tree. Next, we have to choose the least weight. While considering the least weight, it should not supposed to create a cycle. Likewise, we have to choose the edges, and we are just creating the minimum spanning tree. I think it will be understand to everyone. Here we have created a minimum spanning with D to E, E to A, then D to B, B to C. Total value of length of this minimum spanning tree is 6, 11, 15, then 20. 20 is the total value of our minimum spanning tree. Then here another example. Actually here we have to find the minimum spanning tree. We have to apply the Kruskal algorithm. So they given the values here. It's already containing cycles. So we have to remove these cycles in the while applying Kruskal algorithm. Then A to B, A to D, then B to E, B to C. Likewise we will be having C to G. Likewise we will be having edges. In these edges we have to choose the minimum edge, right? We have to choose the minimum edge over the graph. So first of all, so which one is the minimum edges? Here we have chosen the minimum edges 1. This is for your understanding purpose. So minimum edges 1. So what are all the values will be connected with 1? It will be taken as the next edge. So B to C is the minimum value. So we just consider that edges. Next, another one edge which contain the least edge is J to I. So J to I is having least edge, that is 1. So we just connected with 1. What is the next least edge? Next least edge is 2. Automatically wherever you are having a 2 value, so those values will be connected with the edges. So what are the where are all 2 is occurring in the sense C to G. C to G, G is 2 is occurring. Then B to E is also 2 is having. So we just taken this. First of all, we have taken I to G. Then we have taken here G to C also. Here we have 2 value. So we just taken here 2. Next here B to E we taken 2 value here. So next least edge is B to E. Next we are going to consider the next least edge, that is 3. Here where is the third edge is available? That means the edge which is having a 3 value L to K, that is L to K is edge will having a 3. So 1 minute. So K to L is 3. So we just having 3. Next E to F. Next after 3, is there any other 3 here? There is no 3 here. So we will be go with the next value, that is 4. 4 is available with E to F. So we are having E to F. E to F we are having with 4. So we just mention here 4. Next what is the next least value in the sense 6. So B to A, here we have a value with B to A. Next least edge is 6 here. So we just consider here B to A. B to A is a least edge. Then next least edge is 6. That is 1 minute. Next least edge is 6, that is our A to D. A to D we just created the least edge. But if we are adding A to D in the sense, it is just creating the cycle. So Kruskal algorithm ensures that while adding the edges, it should not create a cycle and all. So we have to ensure that kindly. So we just backtrack that A to D. We are going to check with the next smaller edge. If I am adding next smaller edge is also 6, so if I am adding A to C is 6 in the sense, automatically it will produce a cycle like this. So it is also wrong over the Kruskal algorithm. So I think we have to remove this, right? So we have removed this edges. Next I am going to consider the next edge. That is C to E. C to E we will be having 6. So next least edge is 6. So if I am adding next edge is C to E, here we will be having 6, but it just producing C to E, E to B, B to C, just will create a cycle over here. So automatically we have to remove this path. So we have to remove C to E. So here we have removed the C to E. Next, what is the next least path in the sense J to L? J to L, what is that? J to L? J to L we will be having 8. After 6 we will be having only 8, right? We don't have any 7 and all. So we just consider the next least path, that is J to L. Our value is 8. Next is F to H. Next path is next to 8 is 10. We don't have a 9 value and all. So we just include here as we just include the next value, that is 10 here. F to H here. Then I think all the vertices are connected each other, right? All the vertices are connected each other. First of all, just creating just a minimum spanning tree, right? Without any cycle, it just creating the by using least edge, it just created the minimum spanning tree. So it is a good one. So this is another example for creating the minimum spanning tree. Next one is Prim's algorithm. Prim's algorithm is also one of the example for minimum spanning tree. But there is a difference between Prim's and Kruskal algorithm. Prim's consider the vertices, whereas Kruskal consider edges. This is a main difference between Prim's and Kruskal algorithm. Actually, we will be having in Prim's algorithm we are focusing on vertices, and Kruskal algorithm will be focusing on edges. Then as usual in Prim's algorithm we will be having starting with the tree. In the tree we will be having a root node. Then you have to select the arc. That means you have to select the edge, that is least edge. Least edge. Then if there is arc equal or randomly least compared to other edges, we have to choose that. Here just consider that we have to choose the vertices instead of edges. That is what our Prim's algorithm. So choose any vertex to start. Select the arc of least weight that joins a vertex that is already in the tree to vertex that is not in the tree. If there is a choice of arc equal weight, then choose randomly. Then first of all we have to start with A. A to E. A to E we will be having 5. Next E to D we will be having 4. Next D to B. Here we, instead of vertices, we just considering the instead of edges we just considering the vertices. That is what Prim's algorithm. Next we just adding after D to B, we just adding B to C. After that we just adding all vertices are now connected with each other. So minimum spanning tree of this is 20. So already in Kruskal algorithm also minimum spanning tree we have produced as 20, right? So this is an example for creating a Prim's algorithm. Same here we will automatically we will be starting with A. Then A to B is 6. Then B to C, here B to C is 1. Then next we are going to choose B to E. B to E is 2. Then next we are going to choose C to D. C to D is 2. Next we are adding C to G. C to G is 2. Next we are adding G to I. G to I is 2. Next we are adding I to J. We reached G to I. From I we will be having a very least edge is 1. So we choose an I to J. Then from E to F we will be chosen 4. Then J to L we will be chosen 8. Then L to K we chosen 3. Automatically it just produce the minimum spanning tree. So the minimum weight of this graph is 41. So it is also one of the example for Prim's algorithm. So for understanding purpose we can have this graph. You just check with this graph. So we have to start with any vertex and we have to add the values. We have to choose the vertices based on the values. Next we will be having another algorithm called Digital's algorithm. Digital's algorithm also will be using for finding shortest path. Digital's algorithm, first of all we will be having label the node as S with final label, then record the working value at every vertex Y which is directly connected to the vertex. Then look at the working values at the vertices without final labels. So uses of these are all the examples for uses of applications of Digital's algorithm. Digital's algorithm is for finding shortest path. Then internet protocol routing. We have in computer we will be having a concept called open shortest path. First that will be also helpful by using Digital's algorithm. We can apply those concepts. Then telecommunication networks to find the least cost for finding the route communication. Then modeling the spread of viruses to determine how fast virus is spreading over the network. That is also one of the application of Digital's algorithm. These are all the example. This both graph are same here. Here also we will be having B node here. There also we will be having B. So both are we can. It is not compulsory that you should have node here. Node like that only. We instead of node we will be having boxes like this also. Both are same here. Next one is Fourier's algorithm. After Dijkstra's algorithm, Dijkstra's algorithm is also one of the finding shortest path, right? Then Fourier's algorithm. Fourier's algorithm is also for finding the shortest path algorithm. Actually, it will be construct the table. It will be identify whether there is any intermediate label is available within the nodes or not. If it is an intermediate label is available, by using that intermediate label, it will be replace the very least path over here. So first of all, it will be having distance table and root table. In the first iteration, it will be copy the first row as well as first column into the distance table and root table. Then it will be check the intermediate position, x plus y greater than or equal to z, x plus y less than z. Based on this two condition, it will be choose the very least path. Based on this condition, it's just choosing the very least path. That is what we are calling as a Fourier's algorithm. In this Fourier's algorithm, the same method is following here. Here we will be having we just for example in this graph we just comparing BC with the sum of corresponding values in the first one column. The sum is less than existing value, so it we just replacing it. If it is not sum is not less in the sense, we will not do the replacement. Like that we will be doing this process. Next, based on the replacement, we will be doing sorting. Here, based on the replacement, we will be find the best path over the graph. That is what we are calling as a Fourier's algorithm. Here, as a value has changed, replace C with A in the root table and continue for the another path. This is the example for Fourier's algorithm. So these are the example. Here we just constructed the matrix table. In this table we will be identifying based on the intermediate nodes, we will be identifying the best value value. These are all the example for distance table and root table. So thank you all for patient listening. Thank you.